Number theory, lecture 18. And what I'm going to go over again today is Euler's theorem and a special case, which is Fermat's theorem. Fermat was French, so you don't pronounce the T, and Euler was Swiss, and I don't know how it would be pronounced in Swiss, French, or German, but it's always pronounced Euler. And so this is one of the great theorems in number theory and in a lot of applied mathematics. And it says the following: let M be a positive integer and let A be an integer relatively prime to M. That is, the greatest common divisor of A and M is equal to 1. Then, if you take A and raise to the power phi of M and subtract 1, you get a number divisible by M, or in the language of congruences, A to the power phi of M is congruent to 1 mod M, where phi of M, of course, is the Euler phi function. So this is the great result, and a special case is Fermat's theorem. Fermat's theorem is the case when the modulus M is a prime number P. And phi of P is P minus 1 for every prime. In fact, an integer is prime if and only if phi of that number is the number minus 1. So what the Euler theorem says in this case is that if A and P are relatively prime, that is, P does not divide A, then A to the phi of P, that's P minus 1, is congruent to 1 mod P. So this is Fermat's theorem, which we can obtain from Euler's theorem by just choosing the modulus M to be a prime. So for example, if you take, actually, let's make a little table because it's kind of interesting. Suppose I take P equals 7. So phi of P is 6. So A and 7 are relatively prime if and only if A is congruent to 1, 2, 3, 4, 5, or 6 mod 7. These are the congruence classes relatively prime to 7. So for each of these, let's just check the congruence. So for each A, I want to compute A to the P minus 1 mod P. So I want to compute for each A, I want to compute A to the 6th mod 7. Let me do that for all the congruence classes relatively prime to 7. So 1 to the 6th is 1. It's certainly congruent to 1 mod 7. 2 to the 6th, what is 2 to the 6th? 2 to the 6th is 64. 64 minus 1 is 63, which is 7 times 9. So 64 is congruent to 1 mod 7. What is 3 to the 6th? Well, 3 to the 6th is a tad harder to calculate. 3 to the power 6 is 729. 729 minus 1 is 728. And if you divide that by 7, it's easy to see you get 104. So 729 is congruent to 1 mod 7. What about 4 to the 6th? Well, I could take 4 to the 6th power. Let me just do it. 4 to the 6th is 2 to the 12th is 1024. I think it's 4,096. 4,096 minus 1 is 4,095. You divide that by 7, you get exactly 585 with no remainder. So this is congruent to 1 mod 7. Of course, an alternate way to do this, you could say 4 is congruent to minus 3 mod 7. So 4 to the 6th is minus 3 to the 6th. Minus 1 to the 6th is 1 is 3 to the 6th. And we already saw that's 1 mod 7. That's just another way to do it. What about 5 to the 6th? Again, you can say that 5 is congruent to minus 2 mod 7. So 5 to the 6th is congruent to minus 2 to the 6th. Is congruent to 2 to the 6th. We already know that's 1. Let's just actually do it the hard way. If I raise 5 to the power 6, that's 15,625. 15,625 minus 1 is 15,624. If I divide that by 7, that goes exactly 2,232 times. So this is congruent to 1 mod 7. And finally with 6, again, 6 is congruent to minus 1. So 6 to the 6th is minus 1 to the 6th, is 1 to the 6th is 1 mod 7. Or, again, I could do it the hard way. 6 to the power 6 is 46,656. 46,656 minus 1 is 46,655. If I divide that by 7, that goes evenly. It's exactly 7 times 6,665. So this is congruent to 1 mod 7. So we have this nice table which confirms Fermat's theorem in the case of the prime p equal to 7. Okay. And maybe just as an exercise for you to do right now, suppose we take another prime, say p equal to 13. Show that what is phi of 13 is 12. So 2 to the 12 has to be congruent to 1 mod 13. So if you pause for a minute and with a pencil and paper or calculator, just check that this is correct. Okay? Just check that that is a true statement. And I'll pause for a moment too. So this means that 2 to the 12th minus 1 divided by 13 is some integer. Okay. Anyone find the integer? I think it turns out to be, 315. So this is not a decimal or an improper or a fraction, other than it's a whole number. It's a positive integer. Okay. So this is Euler's theorem. How do we prove it? Right. So Euler's theorem, if A and M are relatively prime, then A to the phi of M is congruent to 1 mod M. And the proof goes as follows. So there are exactly phi of M congruence classes mod M relatively prime to M. Or I could equally well say there are phi of M integers in the set from 1 up to M that are relatively prime to M. And if I choose them, or if I choose one representative of each congruence class, we have what is called a reduced system of residues, that R1, R2, R3, up to R sub phi of M be a reduced system of residues modulo M. That means that each of these numbers Ri, each of the Ri and M are relatively prime for I going from 1 up to phi of M. And Ri is different from Rj mod M, not congruent mod M, if we take two different numbers. If I is different from j, say 1 less than or equal to I, strictly less than j, less than or equal to phi of M. So this is the definition of a reduced system of residues mod M. And we can also say the following, note or recall. If A is relatively prime to M, and R is relatively prime to M, then A times R, is relatively prime to M. Right? Why is that? Because if the greatest common divisor of AR and M is bigger than 1, then there's a number bigger than 1. So this number is let's call this D. So if the greatest common divisor of AR and M is equal to some number D, which is bigger than 1, then D divides A, R, and M. And it divides both of them. That's the definition of a common divisor. D bigger than 1 means there is a prime P that divides D. So therefore, this prime P divides M, and P divides AR. But if a prime divides a product of two numbers, then by Euler's lemma, by Euclid's lemma, if a prime divides a product, either of two numbers, it divides at least one of them. So P divides A, or P divides R. But then this prime divides both M and A, or both M and R. And that contradicts the fact that M is relatively prime to both A and R. So this is a contradiction. So if A and M are relatively prime and R and M are relatively prime, that implies that AR and M are relatively prime. So if we take this reduced system of residues, R1, R2, up to R sub phi of M, then these are all relatively prime to M, and so is A. So AR1, AR2, up to AR sub phi of M. This is also a reduced system of residues because ARI and M are relatively prime for all I, 1 up to phi of M, and they belong to different congruence classes mod M. ARI is congruent to ARJ mod M, then RI is congruent to RJ mod M. You can cancel the A's if A is relatively prime to M. So what this means is that this set of numbers represents every congruence class relatively prime to M, and this set of numbers also does. So therefore, if you multiply these numbers together, AR1, AR2, AR3, up to AR phi of M, these numbers are congruent to these numbers in some other order probably, but congruent, but then the product doesn't matter about, doesn't care about order. This is the product of R1, R2, R3, up to R sub phi of M, mod M. And the left-hand side, I have phi of M terms, so I have A to the phi of M, if I factor that out, R1, R2, R3, up to R phi of M, congruent to R1, R2, R3, up to R phi of M, mod M. So if A to the phi of M times this, congruent to, let's say, 1 times this. But this number is relatively prime to M, so I can cancel it. So A to the phi of M is congruent to 1 mod M. And that's the end of the proof. That's what we needed to prove. And what I use consistently in this proof, let me just isolate it just to make it very clear, is the following observation. If A and M are relatively prime, and AX is congruent to AY mod M, then X is congruent to Y mod M. And the way we prove this proof, if AX is congruent to AY mod M, means M divides the difference, AX minus AY, which is equal to, factor out the A times X minus Y. So M divides A times X minus Y, and A and M are relatively prime. So we put these two facts together again with Euclid's lemma. If M divides a product of two numbers and it's relatively prime to one, it divides the other. So M divides X minus Y, or X is congruent to Y mod M. So this is the fact about congruences that we use here, and we use many, many, many places elsewhere. Right. Any questions about this? Let me give a very sort of concrete example of how this proof worked. Suppose I take P equal to 7. So phi of 7 is 6. So I can take a reduced system of residues just to be the numbers 1, 2, 3, 4, 5, and 6. Suppose I take A equal to 3. So I want to choose A. So I want to show that 3 to the 6 is congruent to 1 mod 7. Right? That's what the Euler-Fermat theorem says. And how do I do that? I take each of these numbers and I multiply it by 3. So 3 times 1 is congruent to 1 mod 7. 3 times 2 is congruent to 6 mod 7. 3 times 3 is congruent to 9 is congruent to 2 mod 7. 3 times 4 is 12 is congruent to 5 mod 7. 3 times 6 is 18 is congruent to 4 mod 7. 3 times 5 is 15 is congruent to 1 mod 7. And 3 times 6 is 18 is congruent to 4 mod 7. So if I take 3 times 1, 3 times 2, 3 times 3, 3 times 4, 3 times 5, and 3 times 6, which is congruent to 1 times 6, 3 times 3 is 2, times 5, 3 to the times 1 is 3, which is congruent to 3. 3 is congruent to 3. 3 times 4 is 5. 3 times 5 is 1. 3 times 6 is 4. So this product is equal to this, which is exactly just a rearranged 1, 2, 3, 4, 5, 6. This is all mod 7. And what do we have here? I have 3 occurring on the left 6 times 1, 2, 3, 4, 5, 6. So 3 to the 6th times this is congruent to this. Cancel them, you get 3 to the 6th is congruent to 1 mod 7. That's exactly the way this proof went. So it's very nice. Okay. Any questions about this? So I want to look at some generalizations or some extensions of this, and also another completely different but very important proof. So we have, first of all, that if A and M are relatively prime, then A to the phi of M is congruent to 1 mod M. And what is called the order of A modulo M is the smallest positive integer D such that A to the D is congruent to 1 mod M. So A to the phi of M is 1, but a smaller number might work. So let's call this the order, as our notation will be the order of A with respect to the modulus M. So the order of A with respect to M, this only works, of course, if A and M are relatively prime. it's at least 1, and it's at most phi of m. So for example, what is the order of 3 mod 7? So if you start taking the powers of 3 to the first is congruent to 3 mod 7. 3 squared is 9, congruent to 2 mod 7. 3 cubed is 27, it's congruent to 6 mod 7. 3 to the fourth is 81, is congruent to 4 mod 7. 3 to the fifth is 243. If you divide that by 7, you get 5 mod 7. 3 to the sixth, well, that's 729. That is congruent to 1 mod 7. So if you look at the powers of 3, the first time the smallest positive power of 3 congruent to 1 mod 7 is 6. So the order of 3 mod 7 is equal to 6, which is, as it turns out, phi of 7. What about 2? What is the order of 2 mod 7? So 2 to the first power is 2 mod 7. 2 squared is 4 mod 7. 2 cubed is 8, which is 1 mod 7. So the first power of 2 congruent to 1 mod 7 is 3. The order of 2 mod 7 is equal to 3. Euler's theorem says that 2 to the 6 is congruent to 1 mod 7. And that's not a contradiction, that's just a fact. But it turns out 6 is not the smallest power of 2 congruent to 1 mod 7. 3 is the smallest power of 2. And we can state another very nice theorem. This is theorem 214. So we have m, a positive integer, and a, an integer relatively prime to m. If the order of a with respect to m is an integer d, then if you have 2 powers of a to the k and a to the l, a to the k is congruent to a to the l mod m, if and only if k is congruent to l mod m, mod d. So if the smallest power of a congruent to 1 mod m is d, then 2 powers are congruent if and only if the difference of the exponents is congruent to L mod. Yeah. So the proof. So we have, first of all, a to the d is congruent to 1 mod m. That's the definition of order. Suppose I take k and L and I divide the difference, let me prove first that, let me prove the proof that if k is congruent to L mod d, then these powers are the same. So this is proof going from right to left. So suppose k is congruent to L mod d. That means that k minus L is divisible by d, so k minus L is dq for some integer q, or k is equal to L plus dq. So that means that a to the k is congruent to a to the L plus dq, because this is all mod m, because k equals, the exponents are the same. But just by the rules of exponents, this is a to the L, a to the dq. Right? A to the sum of two integers is the product of those a to the power, which is a sum, is the product of a to these sum ends. And a to the dq is a to the d to the q. But a to the d is 1, so this is congruent to a to the L times 1 to the q, or a to the L, mod m, and we're done. If k is congruent to L mod d, then a to the k is congruent to a to the L. And let's prove the converse. Suppose a to the k is congruent to a to the L mod m. So to look at the integer k minus L, and you can divide that by d, and you get a quotient plus a remainder, where the remainder is between 0 and d minus 1. This is just the division algorithm. K minus L divided by d gives you a quotient q and a remainder. So a to the k, bring the L to the other side, is a to the L plus dq plus r. Which is the same as a to the L, a to the dq, which is a to the d to the q, times a to the r mod m. A to the L was the same as a to the k. That was our hypothesis. This is a to the k. A to the d is 1. So I can 1 times a to the r mod m. A to the k is relatively prime to m, so I can cancel the a to the k. So a to the r is congruent to 1 mod m. But r is between 0 and d minus 1. And d is the smallest positive integer, such that a to the d is congruent to 1 mod m. So r cannot be positive. So r has to equal 0. And if r equals 0, k minus L is dq, or k is congruent to L mod d. Okay. So I want to pause for a moment and give you a chance to look at this and think about it, perhaps. And also, you should pull up your book if you don't have it and just check. But take a look at this. It's important to spend a few minutes trying to understand this proof. Any questions about this? There's a lot here to think about, and there's even more to think about in what I am about to start. So this is a second approach to Fermat's theorem and Euler's theorem. And it depends on the concept of a group in algebra and number theory, which we already defined at the very beginning of the course. So let me review the definition. So a group is a set G with a binary operation usually it's written as either addition or multiplication, with the following properties. I just say such that. I'll just use a symbol star for the binary operation. A star B. This could be plus or times or whatever, but it's associative. So A times B times C is the same as A times B times C. There's an identity element. So this is for all A, B, and C in the group. There exists an element, it's called E in the group. Under addition, you usually write this as 0. Under multiplication, you usually write this as 1. And this has the property that A times E and E times A is equal to A for all A in the group. And you have inverses. For every A in the group, there exists an element B in the group such that A times B and B times A give you the identity. So there are only these three simple properties that define a group. Some groups, but not all groups, satisfy an additional property. So a group G is called commutative or abelian. So these are synonyms. If in addition, the group satisfies A times B equals B times A for all A, B in the group. So some groups are abelian and some are not. It's just the way it is. But a group does not have to be commutative or abelian, but a group must have a binary operation that is associative. There's an identity element, and every element has an inverse. Right? So that's a group. And a subgroup of a group is a subset that's also a group. So let me so a subgroup of a group G is a subset H of G such that the identity of the group is in H, and if A and B are in H, then the product A times B is in H, and if A is in H, then there is the inverse B in H with A times B equals B times A equals the identity. So for example, Z, the integers, is a group. H equal the even integers is a subgroup. Because the sum, because 0 is even, the sum of two even numbers is even, and if A is even, minus A is even. So this is an additive group and a subgroup. If I take G to be, let's say, R greater than 0, that is the set of all real, positive real numbers. This is a group with multiplication. So this with multiplication is a group, because 1 is the multiplicative identity is positive. The product of two positive numbers is positive. And if A is positive, 1 over A is positive, and that's the multiplicative inverse. And if I take H to be the powers of 2, so this is the positive and negative powers of 2, 1, 2, 4, 8, 16, and so on, a half, a fourth, an eighth, 1/16, and so on. This is a subgroup. It contains 1. The product of two powers of 2 is another power of 2. And the inverse of a power of 2 is a power of 2. So the positive real numbers form a multiplicative group. And within that set, the powers of 2, positive and negative powers, form a subgroup. Any questions about this? Okay. So this is in the notes, theorem 215. Lagrange's theorem. It says that if G is a finite group and H is a subgroup of G, then, and what follows then? So let me give this definition. What is called the order of a group. We talked about the order of an element, powers of an element, mod M. The order of a group, G, is the number of elements in G. Or number of elements is also in mathematics called cardinality. So the cardinality of a group, or the number of elements of the group, is called the order of the group, and it's usually denoted with absolute value signs. So this is the order of a group. It just means how many elements are in the group. These groups are all infinite, but some groups are finite. So for example, if I take the multiplicative group consisting of the numbers 1 and -1, that's a group. It's closed under multiplication. 1 times 1 is 1, -1 times -1 is 1. Every element has an inverse under multiplication. That's a group, and this group has order 2. There are 2 elements. And so that's a nice group. Okay. So what does Lagrange's theorem say? If G is a finite group, that means the order of G is finite. It's a finite number of elements in the group. And H is a subgroup, so it's certainly finite. Then the order of H divides the order of G, right? So order of H, that's a positive integer, divides the order of G. So this is the big result for today, and we'll give a proof that G be a group, and I'll write it multiplicatively. So the binary operation will be written as multiplication. Let X be a non-empty subset of G, not necessarily a subgroup, just any subset. And let A be an element of G. A is an element of G. We define the set A times X to be the set that you get by taking every element in the set X and multiplying it by A. So A times X is the set A times little x for all X and X.
Professor, what's the name of this theorem? What's this?
Lagrange's theorem. It's theorem 215 if you check the book.
Okay.
Lagrange. So for every element in the set capital X, you multiply it by A, that's the set AX. This is another subset of G. And I can define a function, a map or a function, they mean the same thing, F from X to AX by F of little x is A times X. And this function F is a bijection. That means it's 1-to-1 and 1-to. So the cardinality of X, the size of X, and the size of AX are the same. This function establishes a 1-to-1 correspondence between the elements of X and the elements of AX. And in a special case, which is important, if X is a subgroup called H of G, then A times H, what you get by multiplying every element of the set H by A, is called a coset. Of H. So a coset of a subgroup is the set that you get by multiplying every element of the subgroup by a fixed element A in the group. So this proof is introducing a lot of new ideas, and that just means it's going to take a lot of time studying to understand what's going on. So let H be a subgroup of G, and let A be an element of G and B be an element of G. So I take a subgroup of the group G and I take two different elements. So consider the cosets AH and BH. So I have a subgroup H and elements A and B, and I multiply the elements of H by A and by B respectively, and I get these two different cosets. Suppose they have an element in common. So if these two cosets, AH and BH, if the intersection is not the empty set. So remember, this is the intersection of these two sets, right? You have AH, you have BH, and what's common to both of them is the intersection. And this is the empty set. So to say the intersection is not the empty set means there exists an element which is in both of them. So everything in AH is the form A times X. Everything in BH is of the form B times, let's say B times Y. So if AH intersect BH is not empty, that means there exist elements X and Y in H such that AX equals BY. Something in here is also in here. And if AX equals BY, because we're working in a group and every element has an inverse, this means if I multiply by, so I have BY equals AX. Then we multiply by Y inverse. But Y times Y inverse is the identity, so that's B. So then B is A times XY inverse. So for all H in the subgroup H, B times H is A XY inverse H. That's A times XY inverse. This is some element if XY is in H, then no, so XY and H. So X times Y inverse is in H, because H is closed under multiplication taking inverses. And XY inverse H is in H. So this is A times some element of H. So this is in the left coset AH for all H and H. So this means that the whole coset BH is contained in AH. And this is a symmetric argument. I could have written A equals BY X inverse, and we would get that AH is contained in BH. So if two sets have the property that each is contained in the other, that means the sets are equal. So AH equals BH. So this is really very important. Here we have the group G, and we have these different cosets, AH, BH, and so forth. And what we just proved is that if two cosets intersect, then they're equal. So this whole group is divided up into cosets. Every element A is in AH because A is equal to A times the identity. It's in AH. So every element is in some coset. And it follows that the cosets of H partition the group. As if this is the group, we have cosets A1H, A2H, up to some number, let's say A sub RH. Every element in the group is in one and only one of these cosets. So G is in the union A1H, union A2H, union ARH. And the order of G is the number of elements in each of these sets. It's A1H plus A2H plus ARH. But each of these translates of H, each of these cosets has the same number of elements as H. This is equal to R times the order of H. where R is the number of cosets, which is the order of G divided just by this equation. R is the order of G divided by the order of H. And that's what we wanted to prove. Sorry, G is R times H, so the order of H divides the order of G. And R is this, when you divide G by order of G by the order of H, the quotient R is the number of left cosets, which is usually written as G colon H in square brackets, or G mod H, like that, G slash H. But in particular, the order of H divides the order of G. All right. So this is a serious proof. This is, you can spend a week on just trying to understand or learning the nuances of this proof. Let me see if I can give an example. Suppose I take the additive group G to be the congruence classes mod 6. So this consists of the classes 6Z, 1 plus 6Z, 2 plus 6Z, 3 plus 6Z, 4 plus 6Z, 5 plus 6Z, right? The order of G is equal to 6. This additive group consists of 6 congruence classes. Suppose I let H consist of 2 of these congruence classes, 6Z and 3 plus 6Z. This is a subgroup because it's closed under addition. If I have 6Z, 3 plus 6Z, 6Z, 3 plus 6Z, and if I add them, this plus this is 6Z. This is 0 plus 3 is 3 plus 6Z. 3 plus 0 is 3 plus 6Z. 3 plus 6Z plus 6 plus 6Z is 6 plus 6Z, which is 0, which is, right? That's the addition table for this subgroup. This subgroup G has order 2. There are 2 elements in it. So we have G equals 6, H equals 2. 2 divides 6. Right? I mean, they teach you somewhere that 6 is 2 times 3, which in this case would say that the order of the group is the order of the subgroup H, which is 2, times this number we call G mod H, the index. In fact, if we take 6Z, I can divide it up into 3 sets. I have H, which is equal to 6Z and 3 plus 6Z. Then I have 1 plus 6Z plus H. So that's the classes 1 plus 6Z and 4 plus 6Z. That's a coset. And then I have 2 plus 6Z plus H. That's 2 plus 6Z and 5 plus 6Z. So the classes 0, 1, 2, 3, 4, 5, 6, I split them up into 3 sets of 2. These are 0 and 3 mod 6, 1 and 4 mod 6, 2 and 5 mod 6. So G mod H, you can call this a set of left cosets. This is H, 1 plus 6Z plus H, and 2 plus 6Z plus H. This is a collection of 3 elements. Each of these elements consists of 2 subsets. Okay, wow. So this is all in a couple of pages in section 2.5 of the text, the section on Euler's theorem. And I strongly encourage you to study this a lot. Okay. Any questions about this? Okay, that's all for today then.
But
And go
when,
ahead.
when is our next midterm?
Oh, certainly not until December, beginning of December. It'll be after Thanksgiving.
Wait, but that's not gonna be the final, right?
Correct,
So in December we have 2 exams.
correct.
Oh. Okay. All right, thank you. Bye.
Mhm. I mean, it's possible Thanksgiving is actually early this year. Thanksgiving is the 23rd. It's possible it'll be the week after Thanksgiving, the end of November, but I haven't decided yet. But you'll know more than 2 weeks in advance. Any other questions?
Okay.
Okay, thank you all. See you Wednesday.